Let's try one more fun experiment with our blue physicist and our red physicist. Let's suppose that while they're playing this game on a train, a spaceship comes flying past them near the speed of light. We now have three systems to worry about: the physicist on the ground, the physicist on the train, and the ship moving above them in the atmosphere. Things are going to get more convoluted now, so we need to keep track of these three things. We're going to use G for ground, T for train, and S for the ship. What happens to their observations of the velocity of this ship? Well, remember, we're looking at length and time now. Velocity is based on length and time, so I need to think about how the distance transforms, right? So think about a small distance dx that the ship moves, and I need to think about how much time it takes to move that distance. We're going to call that dt. Now, the trick for this is going to be that each of these observers is going to measure a different distance and a different time, just like we saw before. The way those two measurements are going to be related is that the distance that the physicist on the, prime is equal to g. No. The way these distances and times are going to be related is that the distance that the physicist on the train measures is going to equal a symbol called gamma. We'll define what that is in a second, times the distance measured by the physicist on the ground, minus this velocity times the time measured by the physicist on the ground. This gamma here is called the Lorentz factor. We actually just discovered it on the last problem we worked. This is 1 over square root 1 minus v squared over c squared. This is the thing that makes relativity happen. Because if your velocity is very low, if it's very small compared to the speed of light, this denominator is basically 1, your gamma factor is basically 1, and you end up with normal, everyday, big, slow velocity transformations like you're accustomed to. We've also got to transform the time that's measured by the physicist on the train. And so this is going to be gamma times the time as measured by the physicist on the ground minus combination v over c squared times dx as measured by the physicist on the ground. Now, velocity is dx over dt, right? That hasn't changed. Even though the behavior is getting weird, the fundamental definitions are still the same. So in other words, the velocity of the ship as measured by the physicist on the train, right, that's what this VST means. It means the velocity of S as measured by T is going to equal this thing divided by this thing. Well, it's nice that these two gammas cancel for us. So this is going to be dx as measured by the ground minus the velocity. Now, this is the velocity here. So in order to be consistent, we're going to call this the velocity of the train as measured by the ground. So we're going to update this with VTG, velocity of train as measured by ground, times dt as measured by ground. Then we'll divide by this thing here, dt as measured by the ground, minus VTG divided by c squared times dxg. So in other words, that's the stuff that's measured by the person on the train in terms of the stuff that's measured by the person on the ground. Divide everything by dtg. This almost looks like a lot of velocities, right? Because I have a dx over a dt, I have a dx and a dt here. So what we're going to do in order to get everybody on equal footing is divide everybody by dtg, divide this whole thing by dtg. All right, I'm allowed to do that because I'm taking the numerator, dividing it by this, taking the denominator, divided by this. It's the same thing as multiplying by 1. All right, what does that become? Well, I have a dxg over dtg, right? The g's match. Because they match, that's going to be the velocity of the ship as measured from the ground minus velocity of the train as measured from the ground, and this dtg and this dtg cancel. So I'm going to divide that by dtg and a dtg. Those will cancel, give me a 1, minus velocity of the train measured by the ground. Here I've got dtg over dxg over dtg again. So that's going to be the velocity of the ship as measured by the ground, and those both get divided by c squared. That's the thing that gives you the velocity of the ship as measured on the train. Right? VSG minus VTG over 1 minus VTG VSG over c squared. Okay, cool. Let's take a look at this thing piece by piece. If our velocity, if our VTG was much, much less than c, then this thing in the denominator, this is basically 0 because it's so much smaller than c squared, right? C is this enormous number and it's getting squared. So the denominator is going to basically be 1 because it's going to be 1 minus a very, very small number. And so that means VST is going to be VSG minus VTG. This is what you would expect in normal, everyday, big, slow experience. You would just expect the velocities to subtract. This also guarantees you that this outcoming velocity can never be bigger than c, because what will happen is this thing in the denominator is always going to compensate for however big this thing gets, right? So let's suppose that the velocity of the ship as measured from the ground is really fast. Let's suppose it's 9/10 the speed of light. Right? And let's suppose that the velocity of the train as measured from the ground is also really fast. Excuse me. Yeah. Let's suppose the velocity of the train as measured from the ground is actually going in the opposite direction. Let's suppose it's going 0.9 c to the left. So let's have a negative 0.9 c. I'm not sure. In normal everyday experience, you would expect it to just be 0.9 c minus a negative 0.9 c, right? If you do the denominator, you would expect VST to be 0.9 c minus a negative 0.9 c. So you would expect a 1.8 c, but we can't go faster than the speed of light. This is the thing that controls that. So we'd have a 1 minus VTG at negative 0.9 c, a VSG, a 0.9 c, divided by c squared. So all these c's go away. This is why it's useful to measure your velocity in units of the speed of light, because it just cancels with the speed of light down there. So we have a 1.8 c on top and a 1 point, what is that going to be? It's going to be 0.81, 1.81 on the bottom. Oh, look, 1.8 divided by 1.81 is still going to be less than c. So this denominator here is there to enforce the speed limit on the universe.
We can also make a visualization of the velocity addition here. Here we're going to set the speed of light to be 1, just so our velocities are measured in units of the speed of light. So we're going to make 3 ships. We're going to make a red ship, a green ship, and a white ship. They're each going to have a different velocity. They'll move along in the x direction. So I got a 0, a 0.25, and a 0.75. They're each going to get multiplied by c. So all of our velocities are in units of c. And so we're going to create the red ship, the green ship, and the white ship here. They're each going to be a sphere, and they're each going to get their respective velocities. That's all this stuff means. You're just assigning these properties to these spherical objects here. Then what we're going to do, this is a neat thing you can do in GlowScript, is attach an arrow. So I can say attach an arrow to the red ship that's based on its velocity, attach an arrow to the green ship based on its velocity, same thing with the white ship and its velocity. So if you just run this, let's ignore the second half of it for right now. So ignore this bottom part of the screen. So I've got the red ship, the green ship, and the white ship. They've each got their arrows pointing this way. So they are moving based on their velocity. Let's run that again. The white ship's moving faster than the green ship, so it's got a longer arrow and it's covering more ground per unit time. You notice I've got another animation window down here. We've created that using this canvas function. So this first view, we showed the red ship's frame. So you notice the red ship was stationary. Now we're going to show the green ship's frame. The way this works is we want to have the new velocities as measured by green. So this is the velocity of each ship as measured by green as an observer. So we just use the equation that we had on the board a minute ago. We take the moving thing's velocity minus the observer's velocity. So it's red minus green minus green, white minus green. Green is always the observer. And then the first one here is always the thing that's moving over here. Then we take that denominator, right? The denominator is the thing that makes it relativistic. So we take 1 minus the red velocity times the green velocity. These things are vectors, and you can't just multiply vectors together willy-nilly. You have to take a dot product. So we're just taking the dot product here between red velocity and green velocity, and then dividing by c squared, just like we had in the equation here. So now we're making new ships. We're making a new red ship, a new green ship, and a new white ship to go in the green ship's reference frame. So because I'm now under this new canvas, these are now going to go in that second window that we have. So I'll make a sphere for each of these, give them their respective colors, and give them their new velocities. We're also going to attach an arrow to each of them to show me the velocity for each of them. And then when you run it, you notice that green is now stationary because you are always stationary in your own reference frame. So green is always going to measure green as stationary. Because red measured green is moving to the right, green is going to measure red as moving to the left. And you notice that it's seeing white moving to the right, but it doesn't have quite the same velocity that it had before. In order to create that animation, we have set up what's called a loop. The idea behind a loop is that it's going to run as long as you tell it to. What I'm telling it to do, I want you to run while white ship's position is less than 2. So this is saying as long as white ship's position's x value is less than 2, so before it reaches the x equal 2 mark, you are going to keep running. The colon here just means I'm signaling that there's a loop below, and the indentations, you notice how all these lines are indented? That means that we are looking at repeating these instructions. So this is the stuff that is considered inside the loop. As soon as you make a line that's no longer indented, let's suppose we add in, let's say print I am finished here. Notice this one is not indented. That means it's not inside the loop. These folks are indented, meaning they are inside the loop. So the indented stuff is the stuff that's going to get repeated. This is the thing that's not going to get repeated. It's only going to happen after the loop finishes. So if you wanted to add some things, maybe you want to animate the white ship's reference frame, you have to make sure you indent to make sure it goes inside the loop. So what we're going to do, we're going to set up an animation right here that just controls the speed of the animation. You do not need to change that line. Here we are animating red ship's reference frame. So we're doing the same thing we did in the position update before. We're taking the old position and adding to it the red ship velocity times dt. Again, this is just delta x equals v times delta t. This is just the change in position is equal to the velocity times the change in time. We're writing it a little bit different here. We're using this plus equals operator. Plus equals is the same thing as add to. So you could write x equals x plus 1. It's the same thing as writing x plus equals 1. You're saying add this thing to this thing over here and save the new value. That's all that means. Then we're going to do the same thing here. We're going to animate the green ship we're going to animate everybody in the green ship's reference frame. You notice though that our time steps have to be different. Our dt here can't be the same dt as here because of time dilation. So we're using the time dilation formula here. We're taking the new dt equals the proper dt divided by square root 1 minus the difference in their velocity squared over c squared. This is time dilation all over again. We have to have that to update our animation. And so here we get two different animation frames. The other thing I've added here is a photon, right? A photon measures, a photon travels at the same speed in both reference frames. So even though white doesn't quite make it as far as it did up here, the photon makes it the same distance. So you can play around with this. You can change these velocities. Maybe you want white's velocity to go much faster. Maybe you want to go closer to the speed of light. Control 2. You'll notice that white gets much farther here than it did before, and it's kind of neck and neck between the two reference frames. But maybe you want to exaggerate the difference there. Maybe you want to make this lower and make this a 0.30, so make it really close to green's velocity. Control 2. You notice that in red's reference frame, white and green, they're moving very close to the same velocity, right? One's 0.3 and one's 0.25. So this one is moving about the same distance. This one, you also see that white hardly moves in green's reference frame, right? So you can play around with this to see how those reference frames change. You can even change this thing to where maybe one of them moves in the vertical direction. So maybe green moves upwards. So let's say we give it a 0.5 velocity in the y component there. Run the code. And what you'll see now is that red in green's reference frame has to move down and to the left because green in red's reference frame is moving up and to the right. You can also see the effect that has on white's velocity here. You notice it's going to be moving downward now to compensate for green's upward motion there. So then the last part of the activity over here on Google Colab asks you to incorporate the velocity transformation along with length contraction and time dilation. So suppose you and your lab partner see a rocket ship pass by overhead and you measure its velocity as rocket velocity over c. What does your partner measure it as? Well, you'll need to do a couple things. First, you'll need to add a slider for rocket velocity over c. Then you'll need to add the calculation of the new velocity, of the velocity that your partner observes based on this calculation here. So you need to add a line to the function to calculate the velocity. Also, don't forget to add rocket velocity over c to the function argument. By that, what I mean is up here where you've got proper time, proper length, and v over c, don't forget to add in that rocket velocity as a fourth argument there in the function so that it knows to pass that number on into the function. And so then you'll get that set up. You can play around with that new slider and address some of these questions here, especially as one of your velocities approaches c.